Welcome to the deep dive. Today, we're plunging into a connection you might have absolutely zero reason to suspect exists. We're linking, well, abstract mathematics calculus specifically to something you probably had today: safe food.
That's right. It's quite fascinating, really. We've been looking at sources showing how mathematical integration plays this critical role in food security, specifically through pasteurization.
Yeah.
For milk, juice, things like that.
Okay, yeah, let's get straight into it then. Our mission for this deep dive. Basically, to figure out exactly how this seemingly abstract math concept helps calculate the heat needed to make our food safe from, nasty microbes.
Right. Think about pasteurization. The aim is killing pathogens with heat. Simple enough, right? But, well, it's not just about hitting one super high temperature instantly. Food flows through heating systems, and the temperature it hits, or maybe how fast it flows, that can vary just slightly, maybe, but it varies over time or even along the path it takes.
Okay, yeah. And the microbes themselves, they don't just poof, disappear instantly. Killing them depends on both the temperature and how long they're actually exposed to it. It's the total cumulative hit that counts.
Exactly. That cumulative effect, sometimes called lethality, isn't a straight line if the temperature isn't perfectly steady. Because, the rate microbes die off changes with heat. Hotter means faster killing. And if the temperature itself is fluctuating a bit as the food moves, well, how do you add up the total killing power through that whole process?
Ah, okay, I see where this is going. Here comes the math, right? This is where sources point. You need a method to sum up that kill rate, even though it's changing constantly over the entire time the food is in that hot zone. Sounds very much like a job for integration.
Precisely. Integration is the mathematical tool for exactly that, calculating the total effect when a rate is changing. So in this case, it lets engineers figure out the total thermal dose, or the total lethality, basically. It accounts for all those little variations in temperature and flow rate you get in the real-world system.
Yeah. Right. So you're not just saying, okay, it hits 72 degrees Celsius. You're calculating the integral, the sum of that temperature effect over the whole exposure time, which tells you exactly how much microbial killing you actually achieved. It's like summing the area under the curve, yeah, where that curve is the kill rate changing over time.
You got it. And this isn't just like theoretical neatness. It's absolutely fundamental for food safety. If you just relied on, say, the peak temperature or maybe a simple average, you could easily get it wrong, underestimate the time needed, and potentially leave dangerous pathogens in the food.
Heck.
Integration lets you calculate the precise total exposure required to meet safety standards. It handles that variability.
Wow, that really connects something from, maybe a tough calculus class directly to whether our food supply is reliable and safe. It's kind of a hidden mathematical layer of safety.
It absolutely is. It just shows how these abstract mathematical ideas can have really profound, even life-saving applications in the real world. It's not just solving for X. It's about building systems that genuinely protect public health, on a huge scale.
Definitely. It supports the trust we place in so many everyday products without even thinking about it. So, wrapping this up then, what's the main takeaway for you listening?
Well, it means that the safety and quality of your milk or juice this morning, it's partly thanks to someone using mathematical integration, using it to fine-tune that heat treatment perfectly.
Yeah, it's a great reminder that even really abstract concepts can be, well, foundational to the practical stuff all around us.
So here's something to think about. Next time you maybe see an integral sign or just enjoy something safely pasteurized. Remember, there's some serious math working behind the scenes. It makes you wonder, doesn't it? What other everyday things rely on complex math we don't even notice, just quietly keeping things working and safe?